Alright, start with variables and units. Alright, so what does capital E stand for? Energy that would be measured in what units? Joules. Right. How about capital W as a variable? Work also because guys following here. You guys know this AP exam's coming in a few weeks. It's final review right here.
No.
Alright, so work is the transfer of energy. Alright, you got potential energy, spring potential, kinetic energy. Guys, notice both of these. Go back a little bit here. There's if you see the term potential energy out of context, they might be referring to gravitational or spring or both. So I've seen if you do that. All right, here's energy in motion. Those things rotating. Okay. Guys, what is capital P as
Power.
power. And what's that measured in?
It's in something.
Watts. Guys, what is 1 watt? Guys, everybody look up here. Look up here. What is 1 watt? What is a watt? How about energy per time? Like joules per second? Right, joules per second? Right, you guys see like a 40-watt light bulb? Right, 40 joules per second? Right. Guys, is this W here and this W here two totally different things?
Yeah.
Those two totally different things. Careful about that. One's a variable, one's a unit. Right, and then we'll look at momentum tomorrow. That's the plan anyway. Alright, energy is measured in what again? Joules, 1 joule breaks down like that. Power is measured in what? Watts. 1 watt is 1 joule per second. Breaks down like that. Alright, so you guys good with the units, variables, units. Alright, so in this class, energy can take different forms. We're focused on a very short list of forms of mechanical energy. So work could be what times what? Force times distance. If you push something with some force for some distance, you've done some work on it. Right? If there's some net force for some distance, there's some net work that's been done. There's some which represents a transfer of energy. Okay. Guys, what is how about this next line? What's this next line? What? MGH? Okay. Oh, I meant to point out to you guys too. Here, let's switch my screen for a moment here. Okay. These formulas we're going down. You should know where to find them on the AP equations page, which you're allowed to use, of course, but it's good to know these anyway. Alright. Here's the universal one. Thank you, Mamar. I round back to that later. That one doesn't show up as much. How about energy in a spring? Guys, look up here. Guys, everybody write in their notes. I want to make sure you guys get this right.
Okay.
Write your notes. What is spring potential energy? There you go. 1/2 kx squared. What is energy in motion? 1/2 mv squared. And if something's rotating, then it's what? I omega squared. 1/2 r. Alright, you guys got all those forms of mechanical energy? Right. Now, energy can take other forms also, like chemical energy, battery, or something, but these are the ones that you can create equations with in this class. Right. Work, force times distance. And if there are two vectors, like force and distance, that are opposite by some angle, you got those times the angle between them. Right. Guys, this is a dot product. You only multiply the parallel components. Right. Oh, and then I got some components for you guys. Alright, so you guys go with dot products. That's a dot product right there. Dot product. Okay. Guys, if you're carrying something up the stairs, does it take energy to lift it vertically? Yeah. Does it take any energy to lift it across the room? Take it across the room? No, because you're not carrying it against the gravity field horizontal to the floor. Alright. Ooh. Alright, what's the area under that curve? Right. Guys, what about this? What if you see a slightly different graph? What if you saw force versus time? What would the area under that represent? Because force versus distance, okay, force times distance, that'd be work. That's what you're looking at. But tomorrow, when you see force versus time, is that impulse? Yeah, or like transfer of momentum. Right, this is a transfer of energy here. Okay, all right, so that'll be for tomorrow. I've never seen AP ask this, but you might see this in college. Blowing up a balloon. Okay, so if you ever see a blow up a balloon, there you go. Spring potential energy. All right, so guys, Hooke's law is that F equals kx. Hooke's law, F equals kx, ideal spring. Okay, and what about the area under this curve? It's gonna be a triangle shape. 1/2 kx squared. You do that. All right, let's get past all this. Don't do that. What does it mean in an energy context when somebody says a closed system? Closed system. Yeah, energy is conserved. So the energy you have in the system that you begin with, end with, has to equate. You can create a conservation of energy equation. Right? Right. And most of the energy equations set up are that classification, a closed system. Right? But guys, what if there's friction that acts on an object? Does that tend to be more of an open type system? Right? And how would you write this? How would you write this? Here, go ahead, write your notes before I flash the answer up here. I want to see if you guys can correctly write what goes in that box. Take a quick trip around the room here.
Because it could be full. Because
you're looking at closed system, which is what you care about most of the time. But sometimes they'll see an open system type question. And how do you handle that? How do you think about that? An open system. Yeah. All right, so you guys get that. I gotta fix. Alright. How many of you guys read that? Show of hands. How many of you guys read that? Yeah. Okay, now everybody knows that, right? Now everybody knows that? Okay. So, guys, classic example is a car breaks to a stop. You'll see this later. I'm going to find out if you know this later. Guys, when the car breaks to a stop, what type of energy does it start with? Definitely kinetic because it's in motion. And most roads are flat, so you'd probably assume the road is flat. There's no height changes, right? So we all just 1/2 m squared, right? By the time the car comes to a complete stop, how much mechanical energy does it have? 0, right? Especially if it hasn't gone up any hills, right? And then, what was the work done by? By what force? Friction between the tires and the road. Force for some distance, braking distance. You'll see that later. That'll be a classic open system. Right. Ooh, Galileo drops the ball from Leaning Tower. That's what type of energy at the top? Oh, and notice this is for the baller system. Yeah, did you guys say MGH for the top? Or potential energy MGH? Hey, now what about 1 millimeter above the ground right here? It's all 1/2 m squared, energy in motion. Right. Now guys, do a derivation right here. Solve for V. Yeah, you guys know what the answer is going to be. But make sure you can tell AP the steps to go from beginning to end. How do you show that?
Justin test.
Let's see if this all has That was not your name.
Oh!
Alright, did you guys say the energy at the beginning equals the energy at the end? So that equals that. And then you guys got what? Your GH. Alright, so did you guys all get that? GH. Alright, guys good. Everybody's good. Alright, new question. Galileo throws the ball. Let's still consider the baller system. This is after the ball is left his hand. Maybe it's just barely left his hand. So it's basically still top of the tower. Okay. Guys, this one's different. Go ahead and solve that whole thing. What type of energy or energy mix at the top? Ooh, it might be more than one type of energy. What type of energy at the bottom? So these variables might need some subscripts.
Oh yeah.
For beginning and ending.
Initial, final.
And then, okay, well, you see what's being solved there is what's the crash speed. So how fast does that ball crash into the ground? Now, while you guys are setting that up and thinking about that, did I specify anywhere on that the angle that he threw the ball? I did not. Did he throw it like maybe 30 degrees down from the horse? I don't know the angle. Right. Turns out, do you think it matters? Do you think it matters the angle that he throws the ball? No. As long as you ignore air drag, yeah, it doesn't matter the angle he threw the ball. Okay. Now, think back to projectile days. There could have been a completely different way to solve that. It'd probably take like 5 times the paper. Where you could break into components and consider horizontal and vertical and yada yada. Right? But we're cutting through all that. We don't even need any of that. All right, what kind of energy did you guys say at the top? Yeah, MGH plus 1/2 m squared. But this V is the throwing speed, isn't it? This is the throwing speed. Versus at the bottom, it's what type of energy? 1/2 mv squared. But this is a different V, isn't it? This is the crash speed. Okay. Guys, which speed is bigger? The throwing speed or the crash speed? Has to be the crash speed. Okay. How do you guys set up the conservation of energy? Oh, in the baller system. Would you consider that to be open or closed? Yeah, closed. You're going with the closed system. First word, ignoring air drag. Common simplification. Okay. Did you guys say that? Did you guys say that? Okay. Now going for the finish. So, well, I think on this presentation I probably skipped a couple of algebra steps from that step to the end. But let me take one more trip around the room and see who can get everything completely correct. Oh, yeah, Oswald got it completely correct. Because there's a common way to miss this. I want to make sure you guys aren't missing this. Close.
Yeah, yeah.
But you're
All right, yeah, I think you got it. All right, some of you guys are getting there. Get there pretty close.
That.
Let's make sure everybody can do the algebra here. Yeah, Jessica got it. Lily got it. Okay. Not quite. Then, yeah, same thing, not quite. Yeah, Schlipp got it. Austin got it. Okay. Yeah, and I think if I gave you guys another minute, probably some more of you guys would get that too. Here, guys, to finish out the algebra. Here, I'm gonna narrow this down. Is the crash speed equal to the throwing speed plus root 2gh? Or is the crash speed equal to the square root of throwing speed squared plus 2gh? Yeah, how about the second thing he said? Okay. Because if you properly follow the algebra between here and here, obviously I skipped a couple of steps. Okay, that's what you should get. Okay, and if you wrote the other way, then that's a common mistake to make. Okay. All right, so you guys get there. And hold on to that idea, because where else have you also seen basically this expression? You guys remember pendulums? What's the speed of a pendulum at the bottom, most point? Okay, it's a very, very similar looking expression. You might see that later. Okay. Ooh, maximum height of a thrown ball. Let's say you're allowed to know how fast you throw it. Okay, so you're allowed to know V naught. You want to know how high is it going to go. Okay. Go ahead, pick a method, either kinematic or energy. Set up an equation and solve for H max. Go ahead. Pick one or the other. Tell me, how high does the ball go based on how fast did you throw it? And if you're a little faster than everybody else, can you also rearrange those variables and get the throwing speed based on how high did the ball go? That could be a good question. So algebra switch around.
It depends.
So you're down at ground level, right? Now, when you release the ball, is it okay? Simplification? Can you say you're basically at height 0 if you're throwing the ball straight up? Yeah. Okay. So let's say you're basically at height 0. So when the ball is leaving your hand down at ground level, it has all what type of energy? Kinetic. Kinetic. And when the ball reaches the maximum height, if you throw it straight up, right, then when the ball reaches its maximum height, what do you know about its energy? It's all gravitational potential. Yeah. You know, if you throw it at some angle and it's like a 2D projectile, that's not exactly true anymore. Okay? But as long as you throw it straight up. Okay? And so here's kinematic. Hey, guys, if you went kinematic, did you choose that one? The one that doesn't say anything about time?
Yeah.
Okay, you can rearrange it like that and then do some algebra and you should get that. So throwing speed squared divided by 2 times the gravity field tells you how high the ball's going to go. Okay, and you know what? Here, well, what about this next line? What about the throwing speed based on the H max? Can you just take this expression and rearrange it and solve for V naught? Oh, look at this! It's root 2gh all over you. Now, if you do the energy method instead, do you think you get the exact same answer?
Yep.
So you guys said at the bottom it's all 1/2 mv squared, the top it's all mg8. So you can solve for H max, and yeah, you get the exact same thing, and then the exact same thing. Same. Alright, there's two methods. Alright, you guys got both of those in your notes. Oh, here's a nice one. Car goes up a hill. But
No.
we're back in the car a bit, but there is a hill. Ooh, there is a hill.
It's so fuzzy.
So you're going up that Virtue Diamond over I-95. You're just coasting. There's no frictional losses. Don't worry about that. Hey, where do you think that car is going faster? At the bottom of the hill or the top of the hill? Yeah, at the bottom of the hill. Yeah. If he's slowing down, it's just going up the hill. Or you could put that in reverse. If it started at the top and then it went to the bottom, it'd definitely be speeding up as it's going down the hill. Works both ways.
Okay.
Alright. Do you guys start with that kind of energy at the bottom? Right. And if I define the lowest point as height 0, then there's no MGH at the bottom. Okay? So it's all 1/2 mv squared at the bottom. And then there's what's going on at the top. Okay? Now, if you had numbers to plug in, like if I told you the speed and the height of the hill and yada yada yada, okay, you could solve for, say, the speed at the top or whatever unknown. Okay? Oh, hey, do you see any variables that might cancel out or could cancel out? The mass of the car? So if you had a little motorcycle next to like a big old Mack truck and they had the same speed, would they have also the same speed at the top of the hill? Yeah. This looks like the mass. It's in all three terms there. Oh! There's a pretty good challenge here. Okay. You guys know the questions the question this all leads up to is what is the speed at the bottom at the very bottom? You guys see it says VF at the very bottom? VF at the very bottom? Okay. There's a geometry portion of this. There's a conservation of energy portion, which is actually pretty similar to what we just did a few slides ago. Okay, do as much as you can on this one. Let's see. Can you do the geometry? Can you do the conservation of energy? Can you do all the algebra?
Is the height.
Yes.
Yeah, you guys see a nice triangle right there? You see a nice triangle, right triangle. That could be helpful. So I remember you guys did a lab on this one. You guys remember you had those speed gates, and you held the speed gates upside down bottom right here. So then you can get an empirical measurement, and then you can compare that to your calculation. And yeah, that was a pretty good lab because all the numbers were lining up. Your measurements and your calculations are all saying the same thing. Well, you guys are still working on that. How about the variable question? You guys see that angle theta from the vertical? Right. What if it was 10 degrees and then you raise that to 20 degrees, 30 degrees, 40 degrees? As you're making that angle bigger, what's happening to the maximum speed at the bottom? Yeah, it's also getting faster, isn't it? Ooh, I think AP might say something about functional dependence. Right, the speed at the bottom is functionally dependent on
It's just
the starting angle.
yeah. It's just
Well, how much time it takes to get to the bottom? As you make that angle bigger, how much time does it take to get to the bottom? The same time? You guys remember from harmonic motion? That's not actually in today's review, but that's a separate question. But today we're mostly focused on the speed. You guys remember T equals 2 pi square root L over G? Yeah. Okay. All right, here we go. What did you guys call? Here, I'll trace this out with my mouse cursor. You guys see this leg of this right triangle right here? What do you guys call this? What times what? L cosine theta? Boom. Right. Okay, so that's L cosine theta. What is this height gap right here? L minus L cosine theta. Is that okay? You guys see that? Okay. And if you want to, could you factor something out of this expression? What could you factor out? L, and then what would that look like? There you go. L times 1 minus cosine theta. Right? Now that's all geometry. We haven't even hit the energy yet. That's just geometry. Can you guys do that geometry? Right? Well, I guess you know, because if you got it, then you know you can. And if you didn't, then you need to study that. All right, let's go over to conservation of energy. Guys, could this be called the Bob Earth system? And that could be a closed system. Right, so we have a nice closed system. What type of energy at the very top? MGH. And then at the bottom,
Oh.
all 1/2 mv squared. Right. Oh, and what is this gray term about? Why did I put this in gray? Yeah, you could give it a push. Yeah. They probably wouldn't do that, but they could. Right. Yeah, so yeah, probably 90% of the time this will not be in there. But 10% of the time. You may throw that in there. Maybe a little push. Okay, can you guys finish off the algebra to solve for this VF right here? Finish off the algebra. Go ahead. You guys, a little time. Can you do all the algebra? Solve for the speed at the bottom.
What do you say?
Solve for VF.
We have L's for the we know it. I don't think it needs it.
Yeah, they just
You
got
you guys
it.
want to hold it.
Yeah, they totally got it.
I really get Disney speak.
Alright, Logan. Chloe got it. Flip got it. Austin got it. Samantha got it. Alright. You guys get it?
Do another code.
Yeah, what is the station?
Yep, another code on it.
Alright, what you guys here?
No. Put
Yeah, Tristan got it. Daniel got it.
No, that's
Alpha got it. Alright. Alright. Sit there. Center got it. Alright. You got it. Alright. Let's guys finish that off correctly. Okay. Oh, and what variable canceled out? The mass of the bob. Mass of the bob. Hey, does this look like Galileo throwing an object off the Leaning Tower?
No.
The crash speed is the square root of the speed squared plus 2gh. Ah, it's a funny looking h. It's just this. Right, you guys can solve the pendulum? Is it for the speed of the pendulum? Speed of the pendulum. Okay. Alright, oh, there's the lab you guys did. You did a calculation, did an empirical measurement. Ooh, I like this one. Alright, so here's the story. We're gonna take this block, some mass m, we're gonna squash it into the spring with the spring constant. And here's how much we smash it, some distance x. That's how much we compress the spring. Then we go, pew! It's gonna fly around this vertical loop. So when it rose to some height to get there. I wonder what's the speed at the top. The speed at the top. And let's say there's no frictional losses. Negligible friction loss. Right, what's the speed at the top? This one I'm just looking for the basic setup. Right, what setup would allow you to answer that question? Can you guys set up a conservation of energy for that right there? Yeah, what type of energy at point A? What type of energy at point B? There's no frictional losses, so it's a closed system. All the energy equates. Okay, so think about this closed system right here. Sum of energy initial equals sum of energy final. What did you guys put at the where's my mouse cursor? What did you guys put for right here? 1/2kx squared. All the energy was stored in the spring. That was the source of all the energy. Maybe it's like 100 joules or whatever. By the time this gets to point B up here at the top of the loop, it's what and also what? Yeah, it took some MGH to get up there. And whatever you have left over, 1/2mv squared. Okay. Hey, you guys do that? Ooh, here's a question I stole straight off some old AP materials. Can you guys create a conservation of energy equation for that situation? Can you guys treat the bungee cord as a what do you guys think you're going to treat the bungee cord as? An ideal spring. Aha, ideal spring. So you guys know the bungee cord is an ideal spring. Can you guys set up a conservation of energy? Looks like the bungee jumper jumped off, and maybe there was like a sidewalk below. You just barely touch the sidewalk, and then the cord pulls them back. You guys notice all these conservation of energy setups. We're going from some point A to some point B, right? Some initial to some final. All right. So we got a closed system. Oh, closed system of what, and what? Guys, I'm thinking of 3 objects in the closed system. What's one object?
The person.
Yeah, how about the person? Looks like, okay. Yeah, this mouse here. Also the what? Also the bungee cord, yeah, or the spring, you can say, right? And what's the third object? The Earth. Aha, the Earth. That could be a closed system. What type of energy did you put at the very top? MGH, right? And the H here is, well, relative to the lowest point that it would be at if I define the size here. So it could be L plus X, couldn't it? Right? And at the second snapshot right here, where'd all the energy go?
Into the bunch.
Into the bungee cord. Ah, which we're treating as an ideal spring. 1/2 kx squared.
You summed up the.
Now, if you had some number of variables, could you solve for whatever? Ooh, guys, how about this? Suppose there's a small person and a heavy person. A small person and a heavy person. Do they stretch the same length? Yes or no? You're right. It would be different lengths because, yeah, the mass does not cancel out. Yeah. I don't think anything quite cancels out. I think everything matters. Ooh. Okay, this one's a little more involved. I do like this one. Okay, guys, you guys, show hands. How many of you guys think you're gonna take physics in college? Who's gonna take physics in college? Okay, you're gonna almost certainly get this question. So let's go through this. What's the minimum roller coaster hill height so that this can get around if there's no frictional losses? Right? So first, I need to address what's the minimum speed to get around. Because guys, what if it peters out right here? What if there's zero speed? Is it ever gonna get around? No, it's just gonna follow the track. Right. And do you guys remember how to solve that? This goes back a few weeks. Actually, right before the spring break. Okay. You guys remember the minimum speed would be square root of GR? And if I cut it off right there, minimum speed squared is GR. Okay? Right. Do you guys remember I had a cup of water on a string and it's wheeled that around in a vertical circle? And a little slower. And they were still minimal speed to get around the top. And that's represented by that. Right. Now that's not energy, but this next part is conservation energy. Okay, is we're going to go from this point A right here at the top of the hill to this point B at the top of the loop, okay, which is going from what type of energy to what type of energy? Yeah, we start off with MGH. Okay. Now, it depends how you define height 0. If I define height 0 as the very bottom right here, the very lowest point, okay, then at point B, it does have some height, and the height is 2r. Okay, so you could say mg2r at the end, where the potential energy. Okay, this is not the only way to set this up, but this is probably the way I would do it. Probably the most common way to set this up. Okay, then hey, I can make a substitution right here. What can I substitute for this v squared? Gr. Oh yeah, because that's the same thing. It's the same thing. Oh yeah. Need a little algebra cleanup here. I'll find some terms maybe. What's one variable that's eventually going to cancel out? The mass. So if you have an empty cart versus a cart full of passengers, does it the same minimum hill height? Yeah.
Oh.
What else could also cancel out? Gravity field. So if you constructed this on the moon, would you still need the same minimum hill height on the moon? Yeah. There you go.
That's a little closer.
Right, there's the classic answer to that very classic question. But more importantly, the process. Are you guys able to follow every step of the process there? Or maybe more importantly, write it down on paper before I explain it? Okay, here's the big important one. You guys know this one keeps coming up. Go ahead. Now, remind you guys too, back a few weeks ago, you guys saw the same title of carburetor at the top. We were looking at so forces and accelerations. This is not exactly that. You're never going to have to solve for the acceleration of the car using an energy method. You'll also never have to solve for how much time it takes for it to stop, even though there is definitely some time interval. Right? But those are variables that you're not going to be writing right now. Yeah, braking distance is the question. Yeah, that's the classic question. What's the braking distance? Kind of where this is all headed towards. Question Henson, you guys, are you going to treat this as a open system or a closed system? Open. I might say a system consisting of only the car. That would be an open system. An open system because is there a net external force acting on the car? You said friction?
So it's good.
Guys, if there's friction and there's some associated stopping distance.
Workforce.
That's me.
How about this? What if it was a dry road versus what if it was a wet road versus what if the road was covered with snow? Do you think those would all be different braking distances?
Yeah.
And if that's true, what character do you think is gonna have to show up somewhere in your derivation? Alright, let's take Palmer, trip around the room here. See how well you guys do.
There you go.
Yeah.
Okay, I think that's it. I think Oswald got it. Alright, tell you what, guys, if you don't think you can get the whole thing, write as much as you can, because if this was a free response question, do you think this might be worth 3 or 4 points? You might be able to pick up 1 or 2 points.
I've done that before.
Oh, okay. Here, guys, can you set a distance equal to an energy term? Is that a thing? Are you allowed to set distance equal to energy? No, those are different concepts. You're allowed to set energy terms to other energy terms. You're allowed to add and subtract energy terms. Are you ever going to set a force equal to an energy term? Is a force equal to a distance?
And we're going the
Alright, so guys, here's your basic framework.
Kinematics.
So open system, you guys said open system. So you have to think of that, right? What type of energy does the car start out with? Kinetic, 1/2 mv squared. Right. What do I how do I write work done by friction? Force times distance. And then what type? How about at the very end? What do I write for the very end? 0. Aha. Right? It's a little closer. Now, I want to substitute out this friction force right here in terms of what and what. Exactly. Guys, coefficient of friction times normal force. Isn't that true? Right. Okay, that's what I was asking before. It said what if roads dry versus wet versus snow. Blah, blah, blah. It has to do with coefficient of friction. Okay. Now, I'll tell you guys too, this next step I actually did skip 1 algebra step. Because normal force is also equivalent to what other force? The weight, as long as it's just a level road. Right? So, can you replace this friction force with coefficient of friction times mg? Is that okay? Ultimately? Okay. So, okay, yeah. Truth be told, I did skip an algebra step from here to here. Okay? But I think you guys can digest that. Okay? Now, all the physics is basically done. Can you finish off with the algebra? Can you solve for D in terms of everything else there? Solve for D. What's that braking distance?
That's what that. I just put a different.
What variable canceled out? Mass of the car. Did you guys get that? Okay. And oftentimes they focus on what relationship. This is proportional to what? Yeah, v squared, right? Okay. Which means if you drive some speed, brake to a stop, measure that. And if you go back with 3 times the speed, guys, 3 times the speed is how many times braking distance? Guys, 3 times the initial speed is how many times the braking distance? 9. 9. This one. Okay, block slides down the incline with friction. Now, guys, ideally you could create that whole free body diagram. There is one thing I'm looking at like, I wish I hadn't typed one thing. Does anybody see it? Does anybody see what's on there that kind of bothers me that I wish I hadn't typed it? You guys see this friction force at Z equals mg sine theta? Is that always true? No, that's not always true. I really wish I had not typed that. Now, that might be true. That's only true under what special circumstance?
Oh, it's equilibrium.
Equilibrium. So what if the block was sliding down at constant speed? Then that would be true. Okay. But that doesn't have to be true. So I really wish I hadn't written that pink. Just ignore that pink. Okay? Ignore that pink. Okay. What do you think goes in this box right here? Friction force equal to what? Yeah, coefficient of friction times normal force. And this normal force is equal to what? mg cosine theta. Alright, so you guys can do all that? All right, step by step. That's not too bad, right? You guys know. What do you think goes in this box right here? Yeah, friction force times stopping distance. In this case, the stopping distance would be the length of this incline here, or if the block slides that length. Okay. Notice it's not the height change or anything like that. Okay, it's like this diagonal length. And since you know the friction force is equal to this whole funny looking expression, can I just sub that in there right there? Like that? Okay. All right, now, how about this gold box? What do you think goes in this gold box? Are you going to treat this as a closed or an open system? Open system? Right. I actually have 2 lines in that box, but I don't want to give away too much too fast. Okay, so go ahead. What do you think goes in that gold box?
Gold box.
Wait.
Gold box.
It's MG.
But it's, yeah, it's still MGH.
All of that.
Because L
Would
is.
you have a high nut and then make some?
Yeah,
Find this
no,
that
I was
big.
thinking the lens extended, this is going on.
That's it.
Alright, you guys ready for a hint? Oh, yeah, we got this phone call. Alright, and we're back recording. Alright, so did you guys use that format right there? You guys did tell me open system, right? Open system? So the energy top, highest work done by friction, is how much energy you end up with at the bottom. Did you guys get that right there? Alright, give you guys a little time to jot that down in your notes. If you need that in your notes.
Do warning equation.
Alright, you guys got that?
Mr. Griffin, can we do a Lorentz equation?
Huh?
Can we do more?
Sorry.
Are we supposed to do anything else with it?
But that's all I have here. But you could do more. What were you thinking? Yeah, you could. Guys, do you guys see what Logan sees? What variable could cancel out? Yeah, the mass of the block could cancel out. Furthermore, guys, is this H related to this L possibly? Guys, how is this H? Guys, let's do some geometry here. How is this H related to this L? Could this H be replaced with L times sine theta? L sine theta? You guys got that?
Oh, I don't like that.
Atwood. A few weeks ago, Atwood, we were looking at forces and accelerations and tensions and yada yada. Right? But now, maybe we're to a very specific approach to the Atwood with energy. Right? Guys, what question would be asked with an Atwood that would lend itself very nicely to conservation of energy approach? Yeah, the velocity of the block after some what moved? Yeah, after some height change or some distance. Exactly. Right. Not speed as a function of time, not how far is a function of. Yeah. If they ask you how fast is one of these blocks moving as a function of the height change, then this is the fastest way to solve that. Not the only way. You could still go dynamics, yada yada, kinematic. M1, M2 or system. Could that be a closed system? There's no frictional losses. Guys, what type of energy at the beginning? Do you guys see this M2 versus this M1? Does M2 look bigger? Do you think it's eventually going to fall down? The fact that it can fall down some height, M2GH, okay, that's sort of the supply of energy. That's where this system gets its energy from to be able to move at all. Okay? And after this has fallen some distance, H, is it still in motion? Is it still going?
Yeah.
Yeah, that's just some arbitrary action. It hasn't hit the floor or anything necessarily. It could still be moving on the move, which means it has what type of energy? Kinetic? But you know what? Yeah, it's a little brother over here. Is this guy also on the move? And furthermore, does this guy have to get lugged up some height change? So how do you finish this off? What? There you go. Okay. You have to lift the small block,
Couldn't we?
and at the end of that motion, they are still in motion, so you have some kinetic energy also. Yes, those are all energy terms. Gravitational potential energy, kinetic energy. It's all energy. Yeah.
If I see a kinematic question.
All right. You guys good on there? Good there?
Apparently I can't.
All right. How about modified?
Like easy.
Is this probably fairly similar? Do you think? Do you think the fact that this M1 is hanging off the edge and it can fall some distance? What do you think goes right here? M1GH. Right? And after it has fallen, let's see, it hasn't quite hit the floor yet, so it's still moving. You have what?
Yeah.
Yeah.
That one.
You got that, bro.
It's what type of energy plus what type of energy? Kinetic and kinetic? Aha. Ah, kinetic.
See, that was what I was gonna say.
Because this top block is now in motion, but it wasn't actually lifted any height change.
No height.
Okay. And if that's if there's no frictional losses.
So much bad.
Oh, if there is frictional loss. Let's throw a little friction here. Look, I have an orange friction vector. Can you see that? Is this now an open system? That's an open system, isn't it? Open system? Okay. So I think this block falling on the right, called block C, is going to provide the energy. Right. Now, as it's moving, friction is dragging and taking energy out of the system. That's worked on by friction. And those are all energy terms. Force times distance, that's work. That's an energy term, basically, right? Energy transfer, right? And you end up with what plus what plus what plus what?
Some G8 plus one.
Yeah, mass A is moving up, and then all three of these blocks would have kinetic energy.
That work.
All right, you guys can do all that? All right, ooh, pulleys. You guys ever create pulleys?
Mechanical.
So working equals workout, mechanical advantage. I don't see APS in too many of these, so it'll be kind of fast. You get mechanical advantage with the wheel. You get mechanical advantage with an incline.
More mechanical advantage.
Ooh. This point could score you some points. Guys, power is what over what? What over what? Work over time, right? Okay, you guys got that? Now, what is work again? What times what? Force times distance?
Which means
And what is distance over time? Alright. Guys, there's a good chance that one of your questions is going to be that on the AP exam. Can you guys get that? Can you guys do that? Alright. Let's do this.
no.
Alright. Asteroid crash speed. Let's treat the asteroid planet system as a closed system. So, guys, what type of energy at the very beginning? Is this asteroid already in motion?
Yeah.
Yes, it is, which means it has kinetic. But is there also some height distance from the planet? But is the gravity field changing while it's in motion? Which means you can't use MGH, you have to use what? Negative GMM over R. Aha. Which looks like that. Right. Now, when the asteroid does crash into the planet, does it still have some distance from the center of the planet? Yeah, and it also moving faster now, isn't it? Like that. There's the basic setup. Okay, you guys see that? Alright, and I think I got a couple slides left here. Oh, yeah, the mass of the asteroid cancels text there.
I'm a station.
And let's just take that. What if the asteroid falls from the edge of space? Falls from the edge of space. You could solve for the crash speed, which would now also represent the escape speed if you go and throw it back up into the sky, which looks like that. Okay. Alright, and last one. So here's the universal form of potential energy. Here's the localized form that we use almost all the time in GH. How does this relate to this? Right? Because the top one is more universal. That's if you have like a potentially changing gravity field. But this bottom one, it's like, well, we're locked in at the surface of the planet. Right? So let's have a small height change, like the height of the leaning tower of Pisa. Okay. So boom, 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 boom. All right, and that is a wrap on energy review.
Museum.